Hello everyone, so thank you for joining me in this particular video, and as we've been doing since the previous videos, I'm going to talk about CNN architectures, and in this particular video I'm going to deal with the residual networks architecture, better known as the ResNet. So essentially, since AlexNet, the SOTA CNN architecture was going deeper and deeper, and hence there was increase in accuracy, but they reached a point where the deep neural networks are now becoming hard to train because of the notorious vanishing gradient problem, which led to saturation in performance, and hence also during back propagation of the gradients, the repeated multiplication was making the gradients infinitely small. So this led to the fact that with the deeper neural networks, there was worse performance in the deep neural networks, and there needed to be a way to tackle this. So the Google Net architecture, which we also have talked about and implemented in a previous video, tried to tackle this problem using auxiliary laws in the middle layers of the architecture. So it did not really tackle this problem once and for all. So hence the core idea of ResNet. So ResNet essentially introduced a concept known as identity shortcut connection, where you skip one or more layers and then you concatenate the earlier layer to the next one or more layers after one or more layers, so in the architecture. So the advantage of skip connections was, one, they mitigated the problem of vanishing gradient by allowing this alternate shortcut path for gradient to flow through. And then the second one, they allowed the model to learn an identity function which ensured that the higher layer will perform at least as good as the lower layer and not worse. So essentially, the higher layer, essentially when we're talking about higher layers, we're talking about the later stages of our architecture, and when we're talking about the lower layers, we are talking about the earlier stages of our architecture. So essentially, I'm going to implement the ResNet architectures using TensorFlow framework. And let me import my custom visualization file. Then I'm also going to import what we'll be needing for implementing the ResNet. So before we start implementing the ResNet, let's look at the residual block, which was the base block which essentially implemented the skip connections. So when we view, there are 5 figures here, but we are going to implement the residual networks architecture using the figure A. So essentially we see that the weight in this case in figure A is essentially in the convolution layer. So we see that before the convolution layer, so there's a skip connection which has been tapped from the input of the convolution layer. Then we see that convolution, we go through a convolution, a batch normalization, a ReLU, then a convolution and a batch normalization, after which the skip connection, which was tapped before the first convolution, is concatenated to the output of the second batch normalization, and then the result is passed through a ReLU operation. So we see that this figure A was the original implementation of the residual block, which implemented the skip connections, but later on we see there have been modifications in the residual blocks of the ResNet architectures, but essentially I'm going to stick with the original one, which I'm going to implement. So let us see deeper how the skip connections are actually implemented in an architecture. So I have 3 figures here. The lower one is for VGG19, which essentially represents the topology of VGG19, which had 19 trainable layers. Then we see now 34 layer plane. So these are actually a plane architecture without skip connections. And then now in the top figure, this is now the topology for the ResNet 34, which essentially implemented the skip connections, where we see that these ones are the skip connections. So the ones with the solid lines are those skip connections that essentially used identity blocks. So the skip connections were being implemented using in two cases. One was using the identity blocks, where it was just an identity mapping of the earlier layer to this part. Now to the skip connection is now concatenated to this layer, but it's actually an identity of an earlier layer. And then for the dashed skip connections, this is where, because of the difference in sizes between the skip connection and the layer it's being concatenated to, there is a convolution block and also a stride of 2 in order to perform downsampling before we concatenate the skip connection and the output of the convolution which the skip connection is being concatenated to. So this one now is the residual block for ResNet 18 and 34. So we see it's actually conv batch normalization ReLU, then conv batch normalization, then we do the concatenation using identity mapping if input and output shapes are same. Otherwise, the skip connection will have to implement a convolution layer if input and output shapes are different. So hence we see that this one is how we initialize our convolution batch normalization and here and batch normalization functions. So essentially they're objects. So then in the call function we implement the topology of the residual blocks. We see convolution batch normalization ReLU, then convolution batch normalization, after which now we want to do our concatenation. So in this case, if we want to use a convolution block, that is if the skip connection is a dashed one, then we'll implement a convolution layer in the skip connection. Otherwise, we'll just take the identity as it is and add it to X. So essentially this one will not run if we essentially don't want a convolution layer in the skip connection, after which the result is passed through a ReLU operation. So this is a residual block. Then after implementing our residual block, now we want to see the architectures for ResNet 18 and 34. So we see that essentially, for instance, if we take this section, this is a convolution operation, but within the convolution operation there's also convolution batch normalization and ReLU. Then the next one is convolution and then batch normalization, after which we now do this operation. So then we see that for ResNet 18 it's 2 by 2 by 2 by 2. So the residual blocks is repeated twice, then here residual blocks repeated twice, here residual blocks repeated twice, and here residual blocks repeated twice. But essentially for the ResNet 34 it's 3 times, then 4 times, then 6 times, then 3 times. So when we go back to here, we see that this is the first 3 up to here, then we go the next 4 up to here, then the next 6 up to here, and then the last 3. So it's 3, 4, 6, then 3. Then we see that only the first stage has not implemented the convolution block in its skip connection. Otherwise, for all the other stages, that's for 4, 6, and 3, the first part of that repetition implements the convolution block in its skip connection. Then the following ones are identity blocks. So essentially, this essentially shows us the fact that there's difference in shapes for the output of the skip connection and the output of this layer to which the concatenation is being done for the two outputs. So essentially that's what we are going to observe when we now implement the res layer for both ResNet 18 and 34. So you see that essentially the architecture starts with the convolution 64 filters, 7x7 kernel size and stride of 2, after which there is a batch normalization and a ReLU. Then there's this max pooling, after which now we go to the residual layers, which are the repetitions of the residual block that we have implemented up here. So essentially this is now what comes before the residual layers. So now when we implement the residual layers, we see that if it's not first block, so for the first instance, for instance, there's here, if it's so it's 3, so there will be 3, then 4, then 6, then 3. So number residuals will be 3, then 4, then 6, then 3. So if for instance it's not the first instance, so for if it's the first block we are dealing with, then this one will not run. We'll just use an identity block in its skip connection for all the repetitions of the zero block. Otherwise if we are, so this one essentially, this one works with the identity for only the first block, else for the proceeding blocks after the first block, proceeding stages, we implement the convolution operation in the first instance, and then the rest are identity. So when we run here, now this is essentially what defines our residual layers for ResNet 18 and 34. Then we see that now for the res layer we have 2, 2, 2 and 2. Then we saw that it starts with the conv, then batch normalization, then ReLU, then max pooling, after which the residual layers, which are the repetitions of the residual blocks, are defined, then followed by the global average pooling, then the dense layer. So we implement ResNet 18 and 34. So now we are done with that one. So let's go to implementation of the ResNet 50, 11 and 152. So we see that essentially for ResNet 18 and 34 we saw that it was conv batch ReLU, then conv batch, then we do the concatenation. But for 50, 11 and 152 we see that now it's 3 convolution layers within the residual block. So then we see that downsampling is done in convolution 3, 4 and 5. So essentially, as we had said earlier, the first stage, the first block of the first stage, essentially we don't do any convolution operation in its skip connection. All of the blocks in the first stage are have their skip connections implemented using the identity blocks. So for the preceding one, for this one, the first block in this stage will implement the convolution block in skip connection, after which the rest will be identity. So here the first one will be convolution, then the next 3 will be identity. Here the first one will be convolution, then the next 5 will be identity. For this one, the first one will be convolution, then the next 2 will be identity. And also another thing, we see that for this convolution, for the 3x3 convolution layer, there is essentially a stride of 2 implemented in that particular layer. So that's what we see here. Now, so essentially this one is the one which implements the identity block in its skip connection. So this is the skip connection, this is the flow, then it's added, then this one implements the convolution in its skip connection, this one, then the skip connection, then we add, then the result. So for both the one implementing identity in skip connection and the one implemented convolution in skip connection, after adding we pass it through a relay operation. So essentially this is the implementation of our block. We see it's conv batch ReLU, conv batch ReLU, of which the second conv is the one having 3 by 3. So this is 1 by 1, this is 3 by 3, then this is 1 by 1, of which this 1 by 1 but 4 times the number of filters as the previous two. As we see here, it's 4 times the number of filters. Then if we want to use a convolution block in skip connection, we essentially do a convolution and a batch norm in the skip connection, after which now we concatenate the result of the skip connection and the result of the normal flow of the operations of the architecture, and then after which we pass through a relay operation. Then the residual layers, this one is the residual layer, of which we see that for the stage of 0 we don't do downsampling, so the stride will remain 1. But for conv blocks, we said conv blocks 3x, 4x and 5x, that's for those stages there will be a stride of 2, essentially because we downsample, then we after which we implement a convolution block in our skip connection. So we see here that for the first stage we use a convolution block, so like not really for the first stage, for first block in the stages after the first stage, that's for stage 2, 3 and 4, that's conv 3x, conv 4x and 5x. It begins with the convolution block, then the rest are identity blocks. So hence that's what is implemented by here. Then we run here, then now implement the ResNet here. For instance, we know that ResNet 50 will be 3463, so we'll pass a list of 3463. So essentially let me go back here, and we see that ResNet 50 is 3463, so we'll pass the numbers as a list of integers. This one we can pass 3, 4, 23, 3, so we'll pass them as a list of integers. So after implementing this one, now essentially we finished with all the implementations of the ResNet architectures, all the way from ResNet 18 to 34 to 50 to 11 to 152. Now we want to instantiate the models and have to build the models in order to get a summary of the models as well as the parameters of the model. So this is ResNet 18, this is ResNet 34, ResNet 50, ResNet 101, ResNet 152, and let's create a dummy rank 4 tensor, and then let's build the models, and then we see the, so we see that essentially ResNet 18 has 11.7 million parameters, ResNet 34 has 21.82 million parameters, ResNet 50 has 25.64 million parameters, ResNet 11 has 44.71 million parameters, and ResNet 152 has 60.42 million parameters. So let us compare it with this number of parameters table which I got from the internet. So you see that essentially we are almost close to the number of parameters in this table. So essentially the difference can come about as a result of the modifications of the residual blocks, as we saw earlier that we used the original implementation of the residual blocks, but there were changes in the residual blocks thereafter. And also so there may be minor details which we essentially did not implement, but we tried our best in order to at least get an understanding of how the residual network can be implemented using the subclass API. So you can also try to modify the residual blocks in order to try to implement the other residual blocks that we essentially did not implement, in order to also have a deeper understanding of how the residual networks was essentially implemented, and also in order to have more understanding on how to use subclass API in order to create custom models. So the last one, we can view the ResNet summary. But yeah, that's all that we have for now. So thank you for watching.